let's use this in an example. So let's see how this would work. So we've picked a direction vector of length 1. We've got a function, we've got a point. Right, so now we've got all the material we need to plug in to find our rate of change.
How do we get the V to cancel out?
The V to cancel.
HG is a length digit stage.
Oh, it's right. So length splits up over products. Alright, so this is this property of scaling. If we take a vector v and stretch it by h,
Okay.
then the length will multiply like that. Yeah.
Just so you know that the length because it's unit vector.
Yeah. Thank you. Yeah. It's the things we left unsaid that are often the most confusing. Right. So what we'll be doing is we'll be heading in this direction towards 1 over root 2, 1 over root 2. We'll be heading at a 45-degree angle through that point. We'll do the setup here. Oh yeah, just one thing I want to say about this notation is that this field is not yet old enough for its notation to have settled down. This was sort of invented only in about 1750, something like that. So its notation hasn't become standard yet. If you look at Stewart, he might write a different notation. Okay, I think Stewart writes this. Right? Something like this. So check Stewart. I like this notation because it sort of feels similar to the partial f, partial x. But this is one of these places where the notation is still kind of fluid and everyone writes something slightly different. Anyway, I'll take the derivative of this in the direction v. So we just plug in all of the pieces to our formula. So we add these two vectors together to get that. Now we'll plug into our actual function f. Okay, I've got two copies of the same expression. This guy's a 2. We'll rewrite it as a 2. And we'll do the algebra up top. Now, when we multiply this in, we'll get a 2. That'll cancel this fellow over here. Okay, now we can cancel the h's, right? Got a common factor of h. Right there. So I'd say this is a fine place to stop. I think that's nice. If if this is reminding you of awful memories of high school algebra or something, we can cancel. Those are equal. So we'll treat them as equal. Yep.
Two square roots, because you multiply 2 times 2 h raised square root 2.
Right, so let's see. Oh, yes, thank you. Right, so this guy, yes, this guy is here. Thank you. Yes, thank you for spotting that. That's huge. Yes, Micah?
Also, shouldn't it be plus h squared over 2?
Let's see. Plus h squared over 2?
Yeah.
Yes, perfect. Yes, nice. These are great contributions. Okay, so it gives us some slope. So what does this number represent? If we were, a little ant standing on the graph of this guy, and we walked in this direction, we would experience a particular slope, a particular rate of change, right? And notice that this rate of change is different, right? If we took the derivative in the direction x, we get 2. If we took the derivative in the direction y, we would also get 2. Right? Take the partial derivative, we get 2x or 2y. But this is like bigger than both of those. Right? This is a steeper direction to climb.
Yeah.
The rate of change
in an arbitrary direction only be the same as with x or y if the direction is the axis?
So for most functions, yes. But imagine that you just had a constant function that just always outputs like 7. Then the rate of change in all directions would be the same, right? So yeah, rate of change being equal to the rate of change of an axis doesn't mean that you live along the axis for sort of constant functions.